Hey curious people, what does a neuron in your brain and a vending machine have in common? A lot. Don't believe me? Let's see how. We can use a tool called a finite state machine to look for clues. Let's tackle an easy example first. Imagine you set out to design a vending machine. You could probably guess and poke around and prod for options. Trial and error sometimes works, right? Yes, and a broken clock is right twice a day. There is an easier way. You have a goal in mind. Collect a fortune in coins by dispensing life-giving cola to night owl junkies in the local dormitory. We need a box to keep the cola safe. You'll need some way for half-asleep students to poke around and get drinks that you want to sell them. As well, you need a way to accept money if we plan for this get-rich part of our scheme to work. Throwing up all the states the vending machine could possibly be in helps our design. Our box can be waiting for coins, selecting a pop, dispensing a pop, releasing coins, holding for more pop, it's empty. We need all the possible transitions there that triggers our machine to move from one state to another. Here's a few lines for the state machine we're thinking of. Has somebody pushed a button? Have they put a coin in yet? Have they put the right number of coins in yet? If no, nothing happens. No Mountain Dew for you. If they have, there's cash in the bank and someone gets a sample delicious syrupy cola. This sort of design diagram can aid us in designing the machinery and logic inside systems of the vending machine. We can be as descriptive of each state as we want. The behavior should not change inside each state without an input or a transition criteria. What stops the motor in the machine from pushing out too many cans? A sensor indicating that something has exited the tray. You may have seen a canning machine where the chocolate bar is stuck and the bar, the little swizzle gear, keeps turning until something finally drops. That's because the state machine for that chocolate vending machine is stuck in the dispense state. For something trivial, you may not need a state machine, but there are lots of applications in our life where it'd be a lot easier to plan things out this way. State machines are used for computer design, chips, electronic circuits, games, and some machinery. The vending machine is a cute example, but this is an AI project blog, so let's bring this back to the topic du jour. We want to emulate a neuron in software, and we can use a state machine to do that. I'd like to compare the model of neurons that live in most deep learning systems today versus the biological neuron. I press upon you that there's a huge difference. There's a huge opportunity to innovate something new once we spy the state machine diagram. The simple diagram you see for an artificial neuron used in deep learning, circa 2022, the model only has two states, accumulating and firing. If we convert this to a functionality view, we see that this is a matrix multiply, a Hubbard product of the weights with the connection statuses, and the output is tied to a threshold function. Many versions use a ReLU function as a firing threshold. The function of an artificial neuron from its state machine, this one, is simple to integrate and fire. It seems suspiciously simple for something that is the building block of a complex system such as the brain. For the biologic example, in the human body, there are a bunch of different types of neurons. Almost all of them are bipolar. They have an input side and an output side. In biology speak, dendrites and axons. The function of a neuron is to interact with other neurons, passing signals. This aligns with the artificial neuron model from before, but when we draw our state machine for a real neuron, we need to look much deeper. You'd be forgiven for thinking of the neuron as a standalone component. In your brain, though, all neurons are suspended in a fluid together, floating noodles in soup.
A three-dimensional snaggle of noodles. Let's zoom in, though. As we pare back some of the mess, we'll see the neurons start to come out and see how they're actually floating together. The round bodies are the centers of the pyramidal neurons, and the lines are the dendrites and axons tying each other together. If we remove some of the detail, we can see that the neurons try to pass each other and connect to each other. The goal of a neuron is to communicate with other neurons.
The inputs and outputs of neurons don't so much connect physically as they send signals across the soup, aka neurotransmitters. Since they all float together, this can have broad effects amongst all of their neighbors. Some neurotransmitters excite the neighbors to fire more easily. Others inhibit the cells to make it harder or impossible for them to fire. Others still make long-term changes to neurons or encourage them to grow, to connect to more things.
And indeed, they do grow. Here's a clip from the Royal Society of an axion actually growing in accelerated time.
One neurotransmitter we all know is dopamine. It enters the soup to reinforce something you need to remember. It encourages neurons to grow. So we have a few more states now: watching, excited, inhibited, collecting, learning, and even forgetting. And seeing as this is a living system, dying. If we imagine a state machine diagram for this biological neuron, it might look like this, with many inputs and outputs and many different states. A biological neuron is a complex, growing chemical sensor machine, a far cry from the simple one shown in the artificial neuron. This should be a clue to you. 1. State machines are a tool you can use to understand systems from chips to networks, neurons, and vending machines. 2. There's a lot of new features we can add to an artificial neural network to take advantage of the way the brain changes states with neurons. The parallel between a vending machine and a neuron is how they rely on states to change behavior. I hope this helped you understand state machines and have some hints on ways you can use them to design systems and think about their states. If you're curious on how this can apply to complex systems, check out the following video on human vision, how the visual world is processed by cells, and how it is nothing close to what a camera is. Stay curious and keep creating. Cheers.